For years, scientists, engineers, and visionaries have imagined the moon as a launch pad for mankind's ventures into the cosmos. Among these dreamers was the legendary physicist Gerard O'Neill, who foresaw a future in which material catapulted from the moon could serve as the foundation for massive orbital habitats. Imagine a lunar mass driver, a powerful, rail-like rocket that propels materials into space at remarkable speeds. This concept promises a future where the moon isn't just a distant body in the night sky, but a stepping stone to greater cosmic exploration. A lunar mass driver isn't just a sci-fi fantasy, it's rooted in the dream of creating a sustainable way into space, a launch system that doesn't rely on conventional rockets and their heavy, expensive fuel loads. While rockets on Earth must overcome immense gravity and a thick atmosphere, a launch from the moon encounters only a fraction of Earth's gravity and no atmosphere, allowing a mass driver to propel materials efficiently and with less energy. In theory, this would allow lunar resources, such as metals and other raw materials, to be launched from the moon's surface and transported to points across the solar system. Imagine how this could transform space exploration. Lunar metals could become the building blocks for space stations, research habitats, or even interstellar ships. We'd have a cosmic supply line with the moon as our launch pad, but achieving such a feat would require overcoming significant technical and physical challenges. A lunar mass driver would have to hurl payloads at a speed of 1.7 kilometers per second to escape the moon's gravity and reach a stable orbit. In practical terms, that's more than 6,100 kilometers per hour, an incredible speed that requires precise engineering, but it's not completely out of reach. Recent research offers a surprising solution to some of these challenges, suggesting that quirks in the moon's gravitational field, called gravity anomalies, could actually help achieve this goal. These lunar gravity anomalies, detected in detail by NASA's GRAIL mission, reveal certain areas on the moon where gravity behaves in unexpected ways, as if influenced by hidden forces below the lunar surface. Normally, gravitational anomalies are problematic for space missions because they disrupt orbits. Satellites around the moon have had to navigate carefully because these gravitational anomalies can cause them to drift unpredictably, risking collisions or unexpected crashes. But according to Dr. Pekka Janhunen of the Finnish Meteorological Institute and Aurora Propulsion Technologies, these gravitational quirks could become valuable assets rather than obstacles. Dr. Janhunen has explored how, by strategically positioning a mass driver near one of these anomalies, we could use the anomaly itself to help maintain a launched payload in lunar orbit for extended periods of time. This shift in perspective, seeing the moon's gravitational anomalies as potential helpers rather than hindrances, opens up new avenues in space infrastructure science. That's where the real potential of a lunar mass driver lies. Dr. Janhunen's research focuses on passive payloads. These are items without onboard propulsion or active navigation. They're essentially objects designed to be launched and then captured or guided to their destination by another system. For example, a payload launched from a lunar gravity driver would ideally remain in orbit long enough for an active tug, a reusable, highly efficient spacecraft, to rendezvous with it and transport it to a processing or construction station in space. The tug could then carry these lunar resources to a station at a strategic point, such as the L5 point, a gravitational sweet spot between the Earth and the Moon. From there, the possibilities are almost limitless. Lunar material could be processed into parts for massive structures, converted into fuel, or used to support a self-sustaining habitat. Traditionally, payloads passively launched from the Moon have orbited for only a short time, typically about a day, before being deorbited back to the surface by gravity. This makes passive launches impractical without extensive orbit corrections, or worse, risks turning them into lunar junk, floating aimlessly in unpredictable orbits. However, Janhunen's research suggests that by targeting specific locations near lunar gravity anomalies, particularly around certain mountain ranges on the near side of the Moon, we could achieve a stable orbit for up to 9 days. This gives the active tug plenty of time to latch onto the payload and transport it safely. Such an extended orbital period could be the key to making a mass driver system on the Moon viable for large-scale resource transport. The mass driver itself, while conceptually simple, is an enormous engineering challenge. A launch speed of 1.7 kilometers per second is no mean feat and requires a power source, precision mechanics, and safety systems capable of withstanding enormous stresses. But the basic technologies we'd need already exist in some form. Advanced electromagnetic launch systems, railguns, and other experimental propulsion methods have shown that these speeds are achievable. With further development, a lunar mass driver could become the backbone of an efficient, low-cost space supply chain. In fact, using these methods could reduce the need for multiple launches from Earth, cutting costs and carbon emissions while opening up new opportunities for large-scale construction in space. Once launched into orbit, these lunar resources would serve as the building blocks of humanity's expansion into the cosmos. A steady supply of materials could lead to the construction of everything from orbital fuel depots to vast habitats and scientific stations. Imagine living in a vast, rotating space habitat made of lunar metals designed to simulate Earth's gravity. This isn't just a hypothetical scenario. Concepts for such structures have been around since the 1970s, when scientists like O'Neill outlined the potential for space habitats large enough to house tens of thousands of people. With a lunar mass driver providing materials, these dreams could begin to take shape. Even transporting fuel, one of the biggest hurdles in space exploration, would become much more feasible. Instead of relying on launches from Earth to resupply fuel depots in space, hydrogen and oxygen could be extracted from the Moon's regolith and water ice, providing a sustainable source of rocket propellant. The cost savings alone could transform the economics of space exploration, allowing far more ambitious missions. Colonizing Mars, exploring the icy moons of Jupiter and Saturn, or even sending probes to distant interstellar destinations. All of these missions would benefit from the logistical support that a lunar-based mass driver could provide. The technical challenges of achieving all this are immense. The lunar environment itself is harsh, with temperature extremes, intense solar radiation, and a lack of atmosphere. Any lunar mass driver would need to be exceptionally resilient, able to withstand these conditions for long periods of time. Its power source would probably have to be solar-based, with arrays able to capture and store energy even during the 2-week lunar night. Shielding of equipment and payloads would be essential to prevent degradation from radiation. The initial setup would be costly and complex, involving numerous robotic assembly missions and remote construction, but the rewards could be revolutionary for space science. Every study, every experiment, and every innovative approach like Jan Hoonen's brings us one step closer to realizing this grand vision. The Moon, once thought of as a distant, barren world, could become our first outpost in the solar system, a place where human ingenuity and determination begin to break the chains of gravity and reach out to the stars. With a lunar mass driver, humanity wouldn't just be looking at the cosmos, we'd finally be stepping into it, ready to forge a future where the universe itself is within our grasp.